All right, so let's get started here. Um, a couple of reminders. So Friday, you guys will take your exam number 2, which covers chapter 4 through 6, and then also should be the same topics in homework 4 through 6. Okay. Um, if you need help preparation, I will be available on Thursday. We can set a Zoom meeting, okay, and then also today afternoon, okay. So also on Wednesday, I think technically I should be also available, okay. So because we have a break on Wednesday, so I don't have class or lab schedule. Just let me know if you need help understanding some of the problems, okay. Um, Number 7 homework is up online now. It's work energy and energy conservation, which is due Thursday next week. Okay, so you guys can start working on that if you feel like you are already prepared for the exam too. Okay, but yeah, you can wait until after you have taken the exam too, and then to start work on that. Okay, so today we'll be just looking at chapter 9, all right, on the momentum and collision. So this one is specifically on linear momentum, okay? And then later on in the semester, we'll be looking at also rotational momentum and collision as well. But for today, we'll be just looking at linear momentum, okay? So in our daily life, if you guys like to watch sports, then for baseball game particularly, when the ball is struck by the bat, so then there's rapid change in velocities, and so some physics concept is involved here. Okay, so we will take a look on this one here, this in this chapter. But you also heard a lot of times people talk about momentum. So for example, momentum of a game or momentum for the election like this happening this year. But that's different than what's defined in physics. Okay, so in physics, momentum is defined specifically, and it's used is represented by a letter P, which is a vector. Okay, so we'll talk about that. But to start with, let's look at the events when you have rapid change in velocity. Okay, so for example, again, if you look at the baseball being hit by a bat here, so the baseball comes in with a very large velocity, right? Very large speed. Um, the good pitcher can pitch like say 90 miles per hour or something like that. That's very crazy fast. But when it's hit, then it also gains a very large speed right afterward, but in the opposite direction or nearly in the opposite direction. So you can see then the change in the baseball's velocity is it's very large. Okay. Also, another example is if you throw a ball to the ground and then it bounces back. Okay, so I think you guys saw this in your earlier homework assignment, one of the problem when the ball is dropped onto the floor, and then when you check on the change in the velocity or when you check at the oscillation, it's a very large number. So that's also a rapid change in velocity. Okay, so in both cases, there's rapid change in velocity. So let's get started with the analyzing of this process when there's a rapid change in the velocity. Okay, so we'll start with Newton's second law here, where it says the force on the object is equal to mass times acceleration, right? And then acceleration is equal to change in velocity divided by time t. So mass times change in velocity divided by time t. Okay, so then we are going to set that F equal to mass times d delta V divided by t. Then multiply both sides by t. So then you get on the left hand side you have force average times t equals to mass times delta V, right? And then delta V, you can write it as V final minus V initial. So it becomes two terms on the right-hand side, force or mass times velocity final minus mass times velocity initial, okay? That equals to F times the T, okay? So then from Newton's second law, we can see that force times T should be equal to mass times V final minus mass times V initial, okay? Now, similarly, to when we define the kinetic energy. So in this case, if you look at m times v, then we'll define that as momentum. Okay, so we're going to take a look on the right hand side of the equation here. So that gives us the definition of momentum in physics. So momentum, you can use letter P to represent it, and then that's equal to mass times V, velocity. So you can see velocity is a vector, so then momentum should be also a vector. Okay. So the SI unit for momentum then comes from the units of mass and velocity. So kilogram times meters per second. That's the SI unit for momentum. All right. So since the mass is a scalar quantity, so then momentum should have the same direction as the velocity. Okay, so they should be having the same direction there. All right, so with that, we can take a quick look what's the magnitude of the momentum for the Earth when it's orbiting around the sun. Okay, so the mass of the Earth is about 5.97 times 10 to the 24 kilograms, and then its orbital radius is a average of, we'll take it as, we'll treat it as a circle, like circular orbit. Okay, as an average radius of 1.5 times 10 to the 11 meters, which is the 1 astronomical units. Okay, that's the definition for 1 astronomical units. It's the distance from the Earth to the Sun. So I ask you to calculate the magnitude of the average linear momentum of the Earth. Okay, so you guys can give it a try. So basically, you just calculate using the scalar quantity of P equal to mv. All right, mass is given, but you have to figure out V by knowing that the for the radius, given the radius, and then the period of the Earth orbiting the Sun should be 1 year, right? So 1 year is 365 days. Okay, so you guys can give it a try. And then if once you have your numbers, you can click on the problem to submit your responses. Okay. All right, so let's take a look as you guys many of you guys have submitted your responses. So you are looking for the just the magnitude. So then P equal to M times V. Okay, so you just take the magnitudes of the mass, it's the scalar, doesn't matter. So the magnitude of the velocity. Okay, so velocity we have to calculate it, right? So velocity, you are given that the period, or you can it's kind of like common sense. The for Earth's orbital is 365 days. Okay, so that's period T, and then linear distance travel should be 2 pi times the radius of the orbit. Okay, so that will give you your velocity. So then momentum P equals to mass times 2 pi r over T. Okay, then you can put in the numbers here. So the mass would be 5.97 times 10 to the 24 in kilograms, and then 2 pi, all right, times the radius, 1.50 times 10 to the 11 meters, okay? Divide by the period of 600 or 365 days, okay? So that's in days. Now you want to multiply by 24, so that's how many hours in a year, and then multiply by 3600, that's how many seconds, okay? So that's 3600 seconds in 1 hour, and then there's 24 hours in 1 day, and then you have 365 days, okay? So you do it that way. So that will give you roughly 1.78 times 10 to the 29th, okay, kilograms meters per second, okay? That's the magnitude of the linear momentum of the Earth, okay? I see most of you guys get this one right. There's a number of 1.19 times 10 to the 18. It looks to me like you forgot about the radius. Okay, so if you get 1.19 times 10 to the 18, then you didn't multiply by the radius r. Okay, all right. If you have questions, you can unmute yourself and speak out. Okay, so if you guys are clear on this one, then we are going to just move on here. Okay, so so basically, if you have we mentioned this earlier, so for Newton's second law, it says net force equal to mass times acceleration. Okay, so then it's actually also defined as so this is the original statement when Newton proposed, so it's equal to the change in momentum over change in time t, okay, or derivative of momentum over dt. Okay, so now we are going to take a look on the left-hand side of the equation that we came up when we analyze Newton's second law for rapid change in velocity. Okay, so on the right-hand side, left-hand side, it says F average times delta t. Okay, so for that quantity, we are going to give it a definition to it. So this is equal to impulse. Okay, so if you have force times delta t, then that gives the impulse to the object. So then impulse should have the same direction as the average force, because average force is a vector, so impulse is also a vector. It should have direction. Okay. So this is the definition for impulse. You can also have differential definition or the derivative of the impulse that should be equal to define as. So if you see 3 lines, then simply also means equals, but it also indicates it's a definition. Okay, so that means always equal to that. So then it's always equal to force times dt. Okay, so take a infinitesimal t, and then that will give you infinitesimal of j of the impulse. Okay, so in this case it would be the force at that moment t. Okay, times that. All right. So if you rewrite that equation we saw earlier, like F times or average force times delta T equal to delta P, by looking at the definition for the momentum. Okay, so then divide both sides by delta t, then you can again come up with this guy, which is Newton's second law in a different expression. Okay, all right. And then for impulse is equal to the average force times delta t. That should be also equal to change in momentum. Okay, so then impulse is equal to change in momentum. So this is the impulse momentum theorem. So it's very similar to the work energy theorem. So work done on the object is equal to the change of the kinetic energy. So here, similarly here, if you have impulse added to the object, then there's momentum change of the object. Okay, so this is the impulse momentum theorem. J equals to delta P. Okay, simply like that. So you can also calculate the J in the different from calculus. Okay, so then so if the force is a varying force, if it's a function of time t, it changes with time t, then you pretty much will have to do integration. Okay, so then impulse is equal to, or in this case, impulse is equal to integration t from initial to final of f t dt. Okay. So if an object receive an impulse, okay, so it depends on what's the initial direction for the momentum, then the final momentum direction will be affected by the impulse received. So for example, if you have initial momentum in this direction and then J comes in this direction, so then final momentum should be in this direction. So it will be J plus P initial, that gives you P final, okay? But realize that this is the vector summation over here, okay? And then J is equal to change in momentum. So PF minus PI, that's delta P, okay? So in the baseball game, you want to change the velocity or the momentum of the baseball rapidly. So there's two ways you can do to achieve this. One way is to give it a very large force, and then another way is to give it larger contact time between the bat and then the ball. Okay, so when the baseball player swings the bat, so then what he does is he increases the contact time t. All right. So for example, if he swings, then increase the time t. So from t0 to 2t, then the impulse delivered to the baseball will be increased by twice. Okay. Just give you an example. Another way you can do is just so if the time t impact time t cannot be changed, then you can apply large force to change to give it a large impulse. So in this case, if there's a collision happens, then the seatbelt will give a very large restraint force to the body. Okay, so to change its momentum. All right. So two ways. One way is to give it a larger force. The other way is to increase the contact time t, delta t. Okay. Um. So impulse and momentum theory. Let's take a look on an example here. I'll have you guys try to solve for this one, and then we can take a look on the solution in a few minutes. Okay. So it says when spiking a volleyball, a player changes the velocity of the ball from 4.2 meters per second to minus 24 meters per second along a certain direction. Okay, so the incoming direction is the positive, and then it comes right back in the opposite direction. It says if the impulse delivered to a ball by the player is minus 9.3 kilograms times meters per second, what's the mass of the volleyball? Okay, so you probably realize that the impulse has the same SI unit as the momentum, right? Because that's due to the impulse and momentum theory. So impulse is equal to momentum change. So then impulse and momentum should have the same SI unit. Okay, so the kilogram times meters per second. Okay, it should be also equal to newtons times second because impulse was defined by force times contact time t. Okay. But yeah, give it a try on this one, and then we can take a look on the solution together. All right. So I have seen your responses here. You can keep submitting if you haven't, but I see a few responses in here. So in here, the ball is given an impulse. Okay, then it's velocity change. So it's the momentum. So you can apply impulse momentum theorem here. And change in momentum, that means mv final minus mv initial, right? So the mass, you can actually single that out. So v final minus v initial. This is a one-dimensional problem because ball travels just in one dimensional. So you can use positive and negative sign to indicate the direction, okay, of the vectors. So for impulse, it's minus 9.3 kilograms times meters per second. That equals to mass times the velocity final, which is negative 24 meters per second minus the initial 4.2 meters per second. Okay, then you simply solve for the mass here. Okay, so the mass should be equal to minus 9.3 kilograms meters per second divided by minus 24 meters per second minus 4.2 meters per second. Okay, so the negative sign basically will cancel out from the numerator and denominator. The result should be 0.33 in kilograms. Okay, so I think all the responses I got here has agreement of 0.33 kilograms. Okay, so good job on that one. All right. Um, So I don't know for how you choose to view the video on my end. So if you pick speaker view, it should be you can have a larger view on that. Okay. Or yeah, I kind of if you couldn't see it, let me know. I can or let me start sharing for momentary, just in case you got a small video view on your end. All right. So let's keep moving on here. So we are going to check on the next section here in this chapter on conservation of linear momentum. Okay, so from the definition of the Newton's second law here, you can see so net force on the object equal to change in momentum over time t. Okay, so if this net force is equal to 0, okay, then change in momentum over change in time t should be equal to 0. Okay, so that means the momentum is not changing, it's constant. Okay, so that gives you the condition for conservation of momentum. So if net force acting on the object is 0, then its momentum is conserved. Okay, so that means final momentum equal to initial momentum. Okay, so if you have a problem that involves that when net force is equal to 0, then you realize that the momentum should conserve. Okay, now in many cases, you might have multiple objects in the system. Okay, so for example, if you have two objects in the system, or maybe more than two, three, etc., then there might be internal forces. That means inside the system, the objects are acting and reacting onto each other. Okay, so but for if you look at one of the particular internal forces, if let's assuming this is a two object system, then if there's one object acting on the other object, right, and then according to Newton's third law, then there should be a reaction force as well. So if you have one object acting on the other object, then the other object will react back on this object, right? So this pair, they have in the same in magnitude for the force pair. This force pair has same magnitude, and then they are in opposite direction. Okay, so these two should add up to be 0, right? Now you can expand this onto more objects if the system has more objects. So um, in that case, you can see if there are internal forces, then they should all add up to be 0 because there's according to Newton's third law, they should be action and reaction pairs. They should cancel out. Okay, so then you only have to focus on all the external forces if there are multiple objects in the system. Okay, so in that case, then if there's multiple objects in the system, if there's no external force on the object, all the external forces cancel out each other, then the momentum for this system of multiple objects should also conserve. Okay, then you can add the momentum of all the object up final. That should be equal to momentum of each of the object adding up initial. Okay, so now realizing that, but keep in mind that although the sum of the momentum should be 0, right? But then each object might have their individual momentum change. Okay, so if you have one object collide on the other one, right? Then basically there's momentum exchange among these two objects. Okay, but for the system of these two objects, then their momentum will be the same. Okay, so you may see like momentum increase in object 1, but increase on object 2. Okay, etc. So for each of the object, they may have change in momentum, but the summation of all the momentum across all the objects, that should remain. Okay, remain constant. Take a look on the collisions of the two cars if that happens. So then initially, so if the car 2 is moving with a slower speed and that's hit by a car 1 that is behind it with a larger speed, then what happens is likely is that car 2 should, after the collision, should gain momentum. So then it will travel at a larger velocity, and then car 1 might have reduced velocity. Okay, but the two cars, their momentum should add up to be constant. Okay, so this total P1 plus P2 should be equal to P1 prime plus P2 prime, which indicate the final of the two momentum. That should be the same. Okay, so but each car have changing in momentum. All right. Also, later on in the semester, you guys will be looking at the collision lab. We'll have two like cars collide onto each other. You can see that in the lab as well. Okay. All right. So I think the previous two slides, when we look at the conservation of momentum, it happens in one dimension. Okay, so for the two car collision or the two cars collide in the lab, they are also in along one line. But in reality, you might have collision happens in two-dimensional, and then sometimes might be in three-dimensional. So then in that case, the conservation of momentum still applies. All right. So let me clarify this. When you have collisions of two objects, okay, then you treat them as one system. So then there's force that given by object 2, given to object 2 by object 1, but there's reaction force from object 2 to object 1. So these two will cancel out. So that's when the collision happens, actually there's no external forces on the system, but if you treat them as one system, then the momentum should conserve. Okay, so whenever you see collision in a problem, then that indicate you can probably apply conservation of momentum. All right, the same here. Now the same here, if you are playing table tennis here, so then for ball 1 hit ball 2, now this happens when this collision happens, actually it will happen likely in two dimensions. Okay, but because it's a collision, so interaction between the two balls, the forces, they are internal forces, so there's no external forces when collision happens. So then the momentum should conserve. Or you can say when the two collide with each other, the external forces compared to the internal forces is very small. So typically external forces are small, and then given the time of the collision, when collision happens, it happens in a very short time of period. So then the effect of the external force can be ignored. Okay, so that gives you the condition that when you see a collision, you can apply conservation of momentum. Okay. All right, so in two-dimensional, when you write out the um, conservation of momentum, then you can write this in vector form, okay? And then in scalar form, you want to write like the momentum in x direction should be equal to momentum 1x plus momentum 2x, okay? P1x, P2x. Initial equal to final. So it's pretty much like P in P1x initial plus P2x initial equals to P1 x final plus P2x final. And then the same for the y direction. Okay, so you want to resolve them into two components. Okay, and then dealing with the conservation of momentum in two dimensions. Okay, so that basically tells you you can actually write out two equations. All right. But I think we are going to just focus on one dimensional for today. So let's take a look on this example here on the collision here. So this one says when the figure shows below, there's a bullet of mass 200 grams. Okay, now pay attention to the unit here. It's 200 grams, so that means 0.2 kilograms. Okay, traveling horizontally towards the east with speed of 400 meters per second. And the bullet strikes a block of mass 1.5 kilogram, which is initially at rest on the frictionless table. After striking the block, the bullet is embedded in the block, and the block and the bullet move together as one unit. Okay, so it's asking you A, what's the magnitude and direction of the velocity of the block and bullet combination immediately after the impact? And then B, what's the magnitude and direction of the impulse by the block on the bullet? C, what's the magnitude and direction of the impulse from the bullet on the block? Okay, so these two should have the same magnitude but in opposite directions, B and C. Indeed, it says if it took 3 milliseconds, ms stands for milliseconds, for the bullet to change the speed from 400 meters per second to the final speed after impact, what's the average force between the block and the bullet during this time? Okay, so I'll give you guys some time to work on this, and then we can take a look on the solution in a few minutes later. Okay. I think I have seen a couple responses in here. We can take a look at the solutions together. Okay, so on this one here, so we need to treat the bullet and the block as one system. Okay, so then the block here, just treat them as one system here. So then for the so the bullet strike the block here. So upon the collision, you can apply conservation of momentum. So that means you can write initial momentum equal to final momentum, or final momentum equal to initial momentum. Doesn't really matter. Okay. Now realizing that this is one-dimensional motion because the two will be just moving in one direction or the horizontal direction. So you can indicate the direction by positive or negative sign here. Now for initial momentum here, you want to put the bullet's momentum plus the block. So block is at rest initially, so that means it's just coming from the bullet. So let me call the bullet as small m, the block as capital M. Okay. So then this is the initial momentum that should be equal to the final momentum of the two. So after the collision, the bullet is being embedded in the block. So then they travel at the same with the same velocity. Okay, so the velocity v. So then you will do small m plus capital M times the v. Okay, so you can set it up this way. Initial momentum equal to final momentum. Then you can solve for the final v here. So v should be equal to mv0 divided by small m plus capital M. Okay. So 0.20 kilograms, right? Times 400 meters per second divided by the 1.5 kilograms plus 0.2 kilograms. Okay, so this will give you your final velocity of the two travel together to be roughly 47.1 meters per second. Okay, so this is the magnitude, and then direction, because it gives you positive, so then that's still in the to the right direction. Okay, so that's positive. Okay, so positive direction there as well. All right. Now on B here, it says what's the magnitude and direction of the impulse by the block on the bullet. Okay, so this is asking for the impulse on the bullet. So then you'll be looking at the impulse for the bullet J bullet. That should equal to small mv final minus mv initial, right? Because impulse equals to the change in momentum. Okay, so then you know the small m. This you can single out the small m, right? So it becomes small m times v minus v0. Okay, so 0.200 kilograms times the v, which is 47.06. So initially, if you keep 4 digits, 4706, okay, minus the initial velocity 400. So this is meters per second. This is also meters per second. Okay, so that gives you minus of 70.6 roughly kilograms times meters per second. Okay, so this is the impulse by the block to the bullet. Okay, now for C here, as I mentioned, so it's asking you for the block, impulse of block, that should be equal to minus of the impulse by the on the bullet. Okay, so these two should be opposite in direction, okay, but the same magnitude. So then it's 70.6 roughly meters per second. Okay. Part D here is asking you if it took 3 milliseconds for the bullet to change speed from 400 meters per second to the final speed after impact, what's the average force? Okay, so on the bullet, if you look at the average force times delta t, the impact time, that should be equal to the j of the bullet, right? So it tells you this guy is 3 milliseconds. So that means 3 times 10 to the minus 3 seconds. what would be the F average? So F average then equals to J of the bullet divided by delta T. So minus 7.6 kilogram times meters per second divided by 3 times 10 to the minus 3 second. Okay, so this will roughly give you so negative sign 2.35 times 10 to the 4. Okay, that should be in newtons. If you look at the if you are solving for the force, that should have SI unit of newtons. Okay, all right. And then on your responses, I think, yeah, looks like you guys all, yeah, you guys got this one right, except like the second responses I got was 80 kilograms times meters per second for the impulse. That might be just a typo because you got the other numbers right. So I would just think that could be a typo there. Okay, but yeah. Any questions you guys might have? All right, so if you are clear, I think I will just stop here for today. Okay, so so tomorrow we will know I will have no class, but on Friday you guys will be taking your exam number 2. Okay, so get prepared for exam 2. All right, and then let me know if you need help. Okay, see you guys on Friday. Bye.